So while my computer is setting up, two really quick announcements. So we finished the grading of your homework 1, and TAs have you graded homework 1 here, which you can collect after the lecture. But the score has been released on Canvas that you can check. And we turn in lab 1. I purposely delay the release of homework 2 so that I can concentrate on lab 1 implementation. So since you submitted lab 1 last night, I have released homework 2 right away this morning. And if you have already looked at the lab, homework 2, you will realize it is quite breadth coverage of problems. 7 problems in total, covering all the stuff we have been talking about since the release of homework 1. And so I do give you plenty of time to work on it. So I will collect your homework 2 back the first Tuesday after the fall break. So you can use about more than 2 weeks to work on homework 2. But that being said, there's a reason I give you that much time is that I want you to work on lab 2 as well in parallel. So I will release lab 2 either later today or tomorrow. Okay. Or maybe I will give you a few days to just work on homework 2 and not releasing lab 2 until early next week. Okay. But then lab 2 will be due after fall break as well. Maybe not on the same date as your homework 2. Maybe a few days later or even a week later than homework 2. The details I'm still trying to look at your schedule and fix that. Okay. And some of you told me that your teammate has dropped the class. If that's the case, you have the choice either finding a new teammate, maybe another person's teammate has also withdrawn from the class. Then two of you can match and form a new team, or alternatively you can work by your own. Okay, that's always an option. And third, I'd like to mention, if we have not finished lab 1, right? If you notice that your teammate is not doing his or her share, you should let me know. Because by default, we give equal share of credit, right? But if you notice a problem with your teammate, like you email him or her and never got any response, he or she is not working on the lab 1 as they are supposed to be doing, then you should let me know, because then this person should not be qualified for the same amount of credit as you do. Okay? So if you notice those issues, do let me know. Okay? You should not keep quiet. You should let me know. If you don't say anything, I will just assume equal share of credit for your lab assignment. Yes, question?
I think mic is off.
Mic is off. Okay. Yes. Thanks. All right. Now it's better. So that being said, let's continue the discussion on hashing. Okay. Okay, so last time we talked about the universal hashing, and quickly remind you what universal hashing is about. So keep in mind, the main objective is to design a good hash function. And as I argued for you in last lecture, deterministic hash function is not going to be good enough. So the setup is you have this game where you have a universe U, which is represented by a domain of size n, and then you have you ask the adversary to choose a subset from you. Okay? But then once this choice is made, so this is the random choice, right? If you think about it. This obviously is a random choice. But once that choice is made, this S is now fixed. Of course, without your knowledge, you don't know S. You don't know any element of S. That makes sense? That's the setup. And the objective is to design a good hash function such that the clearing probability is small. And we formalized all these arguments last lecture, so the idea is to use this construction called universal hashing. So the idea is you have a family of hash function H such that any H from H, small h, any hash function from the family of this hash function is a mapping from this to a domain of M, set M. Okay? Because typically we have the observation that this input domain size is much bigger than your output domain size. Otherwise, hashing is trivial, as I argued again last lecture. Right? So that's the requirement. And the objective is that once you have a fixed set of X, okay, that's the only knowledge you know. You know the adversary has made his or her choice and finalized a fixed set of X, but you don't know anything about X other than this. Okay? The requirement is this probability is over the random choice of this hash function H. You choose one hash function H randomly from this family of hash functions, and the requirement is that this must less equal than this. Which means the clearing probability must less than or equal to 1 over M. And if that's true, this family of hash function is called universal hashing. That's the definition. And I proved to you the expected number of clearing between X and any other elements in S is at most N over M, where this is the setup. Okay, and the proof is here. I didn't go over this proof per se, but I asked you to go over this proof on your own. I'm not going to go over this in class with you, but I do require you to understand the proof. Okay, so you need to go over this proof yourself. Okay, and we talked about how to construct universal hashing. This is where we stopped last time. And I will actually we went over this, but I just want to give you a quick recap. Then I proceed from there for today's lecture. Right? The idea is, suppose n equal to this, and n equal to this. Okay? What you do is you construct a matrix of m by u. So this matrix is m by u. And this is a bitmap matrix. Bitmap matrix, which means every element in this matrix is either 0 or 1. It's a bitmap of matrix. Okay? What you do is very simple. You fill this matrix with random 0 or 1s. So any element in the matrix, you randomly make a choice and select either 0 or 1 to fill in that particular position. And that's your matrix. And you hash function, and of course, every such random choice give you a hash function H. That makes sense? So each matrix, each materialization of this matrix give you a hash function H. So how many hash functions you have in this family of hash function capital H? Can someone argue that for me? Given this matrix, how many hash functions you can construct out of this matrix? Riley? Huh? No? Anyone else? So each instantiation of this matrix gives you a hash function from this family of hash function capital H, right? My question is, what's the size of H here? Michael? I'm asking you this question. What's the size of H in this case? If we're using this matrix to construct our family of hash functions, how many hash functions we have in that family? That's the question.
U times n.
Huh?
U times n.
Sorry?
U times n.
U times n. Okay. Any other attempt? Can you explain to me why is U times n, by the way? U times n give you the size of this matrix, right? But obviously that's not the possibility number of possible hash functions.
2 raised to n times
2 raised of this. Because you have this many positions, each position you have 2 choices. So that's the total number of hash functions you can construct. Okay? And once you have a hash function h out of this, what's your hashing operation? Well, what's your hashing operation? Suppose you have x. What's this x? Remember, x is from the universe u. So x is what? It's 1 by 2 to the power u, because that's what we said, right? The domain size is 2 to the power u. So x is just a 1 by 2 to the power u vector. Does that make sense? Yes? Yes or no? I hope it does. If it doesn't, then you have to spend a little bit of time to think about this, okay? By the way, I do expect you to be a computer science master student, right? I do expect you to understand what is matrix, what's 1 by n vector. If you don't understand even this, then I'm not ready to go back all the way down to 101 to give you a lecture on that, okay?
Aren't we multiplying that matrix by
That's what
x?
we're going to say next. Okay? So
So
it's a dot product between the matrix and this vector. That's the hash function. So your hash function hx is essentially this matrix dot product x. And this matrix is n by u, and this vector is u by 1, by the way. So the output is a vector. What's the output, by the way? The output is a vector of n by 1, which is essentially 2 to the power m. That satisfies this requirement, right? It's a mapping between domain n to domain m. Okay?
up above it says 2 to the u, or 2 raised to the u by. Down there it's u by 1.
Alright. Okay, so this is what we are doing. So this is your output. Output is a vector. This is the vector of n by 1. Right? N by 1 means 2 to the power n. Okay. And it's a dot product between the two. I'm not going to explain what is dot product. I do expect a CS master student to understand this. If you don't understand what's a dot product, you shouldn't be in our master program to begin with. Anyway, we made the admission choice already, so consider yourself lucky and go back to seriously, I'm serious, no kidding. If you don't understand what a dot product is, you should not belong to a computer science master program, period. I will make this claim in front of you, I will make this claim in front of the whole CS students population. Okay. Right. Now, you do a dot product between the two. The only thing I want to specify is the dot product is done with modular of 2. Which means the output at each position is either 0 or 1, obviously, because you are doing modular by 2 operations. And what essentially you do is this pairwise multiply summation that gives you this output. Second row, pairwise multiplication and summation with the entire column get you second row, and so on and so forth. Okay, that's the hash function. And then now the claim. The claim is this is a universal hashing family. This is a universal hashing family. And the requirement is to prove this. So how do you prove this? First of all, do all of you understand at least the construction of this universal hash family? By the way, if you were yesterday, there was a distinguished lecture series. How many of you were there to listen to this distinguished lecture talk? Michael, you were there, right? So the guy essentially, his research, he talked about universal hashing. That make sense? Michael, were you there? Right? He talked about this, and he basically used this in his construction. He actually spent 10-20 minutes to just explain universal hashing, which in my opinion is not necessary, because I do expect the audience to understand universal hashing. Anyway, so that shows it's really a really important construction. The guy is not the guy. The guy is a programming or verification, software verification, formal method type of guy. So this hashing discussion surface go way beyond just database. Okay, way beyond database. So when you claim this is universal hashing family, what do you have to prove? What do you have to prove? Well, you only need to prove this. Does that make sense? You need to prove this. Right? If you can prove this, with regard to this construction, you're done. This construction now is a universal hashing family. But the question is, how do you prove this? Seems like not so easy to prove, right? Not a very easy argument to make. So here is an argument. By the way, this is not the same as saying this is not saying the function is independent. The hash function is independent or uniform. Why? Okay. By the way, this is not equivalent to say this is not equivalent to this. This is not equivalent to this. Okay? The reason is obvious, right? If using this construction, if my x equal to this, meaning this column is all 0, then no matter how you construct your matrix here, the output is guaranteed to be what? To be 0, right? So probability, in that case, probability of H0 is always 1 with respect to the random choice you make. So clearly this special case indicates that this is not the case. Does that make sense? Yes? This is fairly important. Okay? This is a fairly important observation. Because if you have this, you definitely have this. You definitely have this. Right? If you have this, of course, for any x, I have to quantify this properly. If you have this, obviously you can derive this, but from here to here, it's not necessarily true. For this, as an observation I have just made. You follow me? Alright. So how do I prove this? How do I prove this? How do I prove this? Well, the idea is we can think of as adding some of the columns of H, where the 1 bit in X indicates which one to add. Right? That's essentially the definition of dot product. No? We are adding some of the columns of H, where the 1 bit in X indicates which one to add. Take an arbitrary pair of keys, X and Y, such that X not equal to Y, they must differ some places. Because the assumption is X is not equal to Y. Right? By the way, why is adding some columns? Because you are doing this multiplied with this. So this multiplied this plus this multiplied with this, so on and so forth. And the 1 bit here obviously indicates you are adding that column. If it's a 0, meaning you ignore that column. That's it. No? Okay. So X and Y are different. See, in the extreme case, let's say, assuming the worst case. The worst case is what? The worst case is, the closer, the more similar X and Y are, the higher chance you're going to produce a clear, obviously, intuitively, right? So the worst case, they only differ by 1 bit. They are all the same, except only 1 bit. The other cases are even more easier to argue, right? If they differ more than 2 bits, it's even more easier to argue. But let's consider the extreme case where they only differ by 1 bit. Let's say that's the ith bit they differ, which means here is your x, here is your y. They are all the same, except here I'm 1, you're 0. And this is s bit. Okay? So that's your x and y. The rest, I don't care how they look like. You know, as long as they're the same, I don't care how you construct them. Okay? So far so good? Imagine we first choose all h but the ith column. Meaning, remember, a hash function, this, when I say h, when I do this, what you're essentially doing is filling up this matrix with random 0 or 1s. That's essentially what this is doing, right? So far so good? Imagine you fill all the other positions. You fill all the other positions. I don't care how you fill up the other positions. Does that make sense? But then I consider another matrix like that. And no matter how you choose the other values, okay, all the other are the same. And even for this row, let's say we consider the second row, even for this row, it's all the same, except the ith column. Here is ith row, so you should consider the ith column because it's a one-to-one mapping. The ith column, the rest are all the same, except I leave this the last choice I will make. So I make all the other choice randomly, of course. But suppose I do the same choice when I'm constructing these two matrices. So I only leave one choice left. Does that make sense? Yeah. So over the remaining choice of ith column, however, each of the 2 to the power m different settings of ith column give a different value of hy. Do you follow this argument? Because remember, your bit in that column, we flip the corresponding bit in hy. Because you're doing, if this is 0, this is 1, then you are basically flipping the output. And there are 2 to the power m number of choices you have while doing this flipping operation. And 2 to the power m is, so if you don't follow this, check with proof. Okay. Okay. Now, we talk about that's universal hashing. Next, I will talk about something called perfect hashing. And remember, in universal hashing, the clearing probability, as I proved for you, is what? The clearing probability is 1 over m. But the number of expected clearance in a bucket is n over m. Which is actually very easy to argue, right? If you have this, you have total of an element, then its on expectation is just n over m clearance you will see in one given bucket. What does it indicate? From our point of view, that means your query cost is at most what? Oh, not at most. On expectation, your query cost is this. Why? Because that's how many elements you expect to see in a given bucket. So you have to linear scan over that. Right now, I'm in the internal memory model. So every item you have to pay a cost. In external memory setting, this will be divided by your page stack B. How many items you can fit in one page. That's the number of IOs you will pay, right? Does that make sense? So they differ by a factor of B on it, right? So depending on whether you are in memory or external memory. Can we do in the question? Because we do expect that n is typically n is also greater or equal than m, so n over m might still be expected. But still, this is much better because if you don't have universal hashing, what do you expect? In the worst case, this is what you get from universal hashing. Without universal hashing, you get this. Because everything mapped to one bucket. It's still a significant improvement than not using universal hashing. Do you see this? But still, I'm not happy with this. I want to do this. And when you do that, suppose there's a way of doing that. We claim this is what we call perfect hashing. Perfect hashing. Okay? So I'll give you the definition first. Next, I will show you how to construct perfect hashing. Okay? How to construct perfect hashing. Now, first we understand what it is, right? Next, we want to show how to construct perfect hashing. Well, there's a naive solution, which is set m equal to n squared. And then just pick a random h from h and try it out. The claim is, if h is universal, if h is a universal hash family, and n equal to n squared, small n squared, then the probability that when you choose h out of h, that's what that probability random choice is made over. There's no clearing S using small hash function h is at least half. There's no clearing. The probability of no clearing is at least half. Then on expectation, your query cost is just order 1. Because at least half probability, with at least half probability, you have no clearing whatsoever. So on expectation, your query cost is just order 1 is constant. So here is a simple proof of this argument. How many pairs of x and y in S are there? Well, n choose 2, right? Obviously. No? Because size of S is 2, right? Sorry, size of S is n, then you're looking at any pair combination, so that's just n over 2. Sorry, not n over 2, n choose 2. So roughly what's that? That's n squared. N choose 2 is n squared, roughly. For each pair, the chance decline is what? Less than 1 over m. By definition of universal hashing family, right? If you claim capital H is universal, then the clearing probability by definition is less than or equal to 1 over m. So you have this many pairs, and clearing probability is this, and you want this to be less than half, right? What do you set m to? You set m equal to n squared, cancel out, that gives you half. It's a simple argument. Very simple argument. Okay? So now we have a naive solution that gives you perfect hashing. But this naive solution is really expensive because you have to set m equal to n squared. What that means is, if University of Utah try to monitor source and destination IP pairs and count how many packets go to each combination of source and destination IP, my capital N is what? 2 to the power 64. My small n is the distinct number of combinations I have observed. Let's say that's a million. Fairly reasonable, right? A million of different source and destination combinations. For a University of Utah size, this is for University of Utah campus with 50,000 students and faculty, 1 million distinct combinations is not normal. Okay, it's It's not surprising. So small n is 10 to the power 6. What this says is if you want to have no clearance by maintaining this count for each distinct pairs, like how many packets go to each combination of source and destination IPs, and you want to maintain a universal hashing family to do this, you need to set UN equal to 10 to the power 12. Which is fine, but 10 to the power 12 is a huge, huge, huge number. You need to maintain that many buckets. It's too expensive, right? So open question, the next open question is, so we solved this, right? But the next open question is, can we do this in linear space, order n space, linear space? Do you follow my argument so far? Can we do this in linear space? Using only meaning set m equal to this. Set m equal to this. Seems like almost impossible, right? If you think about it, this is a really challenging problem to do. Right? You know you have an input of size n, but you don't know the value of those elements. This is the tricky part. If you know the values, yes, you can do this. Like you make sure each distinct value hashed to a different bucket, right? You know the values. In the worst case, you can do a case statement, right? Case this value do this, this value do this, right? Do you follow my argument? And that's obviously size n, right? But the case statement is almost n case statement. It's because you know small n values. But the point is you don't. You don't know those values. S is a random choice, even though it's fixed, but it is randomly selected from this domain n. If you were to do a case statement, your hash function is size capital n rather than small n. Right? Where you have to case each value and do something. Right? At least order n, maybe bigger than this. So we cannot do that. Without knowing any value in S, we can still somehow do this in linear space and guarantee no clearance. Sounds like magic, seriously. If you ask me, first time I heard perfect hashing, I was like, this is so cool. But it sounds like impossible, right? But you know what? It is possible. And the construction is fairly straightforward. The first level hash function H, is a hierarchical two-level approach. In the first level, you choose a hash function H and a hash table A, a hash table capital A. And then you choose small n number of second level hash functions, and then small n number of second level hash tables. So each hash function in the second level is associated with a corresponding hash table for small n number of them. Small n number of them. To look up an element x, we first compute h x equal to I. You use our first level hash function h to compute which second level hash function to use, and then you find the element in that corresponding hash table, and then we claim this gives you the property we need, which is the clearing probability is at most the clearing probability is very small, and the expectation clearing is just one clearing per bucket in the second level, and the whole construction obviously you can check use only linear space. Of course, you cannot use any hash function. Here is a trick. The first level hash function h must be selected from a universal hash family. You randomly choose one, but you fix that hash function once you make that selection. And all the second level hash functions must be from universal hash family as well. All the second level hash function must be from a universal hashing family as well. Then, as soon as you do that, this whole construction give you a perfect hashing construction. And the proof I will skip. Okay, I will prove that this proof actually is a little bit more involved, much more involved than this argument. But if you're interested, you can look up the proof online and see whether you can understand the proof. But this gives you a perfect hashing construction. However, so far the construction we assume S is fixed, right? So you make the random choice of S, then S is fixed. Does that make sense? This works for most offline scenarios, right? for example, let's use the source and destination IP of the monitoring application for University of Utah. It tells you, okay, I want to count distinct number of package, or total number of package for each distinct the source and destination IP addresses observed for my network from 2000 to 2010. I have all the data, 2000 to 2010. I want you to do this. And this is where S is fixed, right? Because data is historical data, archive data, so S must have been fixed. You just don't know what S is, but S is fixed. You follow my argument? And that's when you can use the perfect hashing construction as we have just discussed. Versus, let's say University of Utah administrator is so impressed with what you do. They hire some company down the valley, they propose a solution that uses N squared, and say, oh, no clearance, University of Utah was happy. Until one day you show up and say, oh, how stupid is that? You can do this in N space. It is stupid, right? Once you realize there's a solution for this versus using a solution of this, then that first solution becomes quote unquote really stupid. Right? So you show up and say, okay, I can do this. And University of Utah said, oh, fantastic. Ditch the other company and go with you. Okay, you make big money, everybody's happy. And then the next day, the administrator said, oh, since you can do such a good job, I'm going to do this in an online fashion, in real time. I want you to monitor the number of packets for each distinct source and destination IP pairs. But I want you to do this in real time, as they are happening over my network. Do you follow me? What's the difference now? What's the challenge now? Well, the problem changed slightly, which is S is no longer fixed. S is still from this universe, right? This universe is 2 to the power 64. Suppose we are using IP4 IP addresses. But S is no longer fixed. Do you follow my argument? And this is what we call dynamic hashing. And we also want, the requirement is very strong. I still need only linear space, and I want to do constant lookup time, meaning I don't want to do this. I want to do this. And how do you construct this? This construction is much more, even the construction becomes much more non-trivial. That I just cannot afford to give you that construction over lecture time. The proof is even more involved. So I'm not going to go into detail. And this is something called cuckoo hashing. A guy from Denmark designed this maybe 8 years ago. So this is a fairly new result, maybe less than 8 years, 6, 7 years ago. Before that, this was a long time open problem. People don't know how, people even questioned whether this is possible until this Denmark guy came along and designed. I forgot why it's called cuckoo hashing. Maybe his last name is Cuckoo. So if you can design something like this, then 10 years down the road, somebody will say, there's a Mike hashing whatever algorithm, right? If your last name is Mike. So cuckoo hashing. I'm not going to go into detail, but that's at least we know what it does. So in the future, if in your job you are required to do this, maintain a hash bucket, linear space, to S, you don't know S, keep in mind S is the dynamic changing set. So even this value N is changing over time, but you want to maintain linear time all the time, linear space all the time, and you want to have constant clearance at most for each bucket. What do? You use cuckoo hashing. If it's static, you don't even have to use cuckoo hashing, you do this. Of course, cuckoo hashing can do this in static case as well, because static case, strictly speaking, is a special case of dynamic hashing, right? But you don't have to use something as complex as cuckoo hashing for static case. That make sense? So all this being said, I still owe you an explanation why I claim I still owe you an explanation why I claim haven't explained to you why this is a good hash function, right? Remember, this is the objective of having this whole discussion, right? So I spent so much time explaining universal hashing, the construction, the proof, perfect hashing, all that stuff. I still haven't touched the core of the problem, which is what I promised you to do. That ax plus b mod p, then bracket mod m is a good hash function. It's not that I don't want to explain this, it's that without the things we have discussed so far, I cannot even start this discussion with you. So finally, we're ready to talk about this. This is the reason why I'm having all this discussion in the first place. Okay? So next, I will explain to you why this is a good hash function. Okay? Do you follow my argument so far? Okay. We're finally ready to do the things we want to do. The point is, in order to try to build a car, you don't go and build a car. You build the engine, you build the wheel first before you build a car. It's nice and bold to try to build a car, but you have to start with something basic. People invent bicycle before people invent car. Keep that in mind. People don't invent airplane first, then come back and invent bicycles. Always the case, right? All right. Now, first of all, I give you a definition. This definition called K universal hashing and K-wise independent hashing. It's a generalization of the universal hashing definition we have. And the definition says the following. Okay, the setup is the same. I have a family of hash function H, capital H. That's my family. And I have a universe U of domain n, capital N, to the power U. And let's say I randomly choose K elements from this universe U. I randomly choose K such elements from U. And K values from the output domain M. And they don't have to be distinct, by the way. I mean, in the output domain, the input must be all distinct. But the output, the K output I choose are not necessarily to be distinct. So meaning you can't have clear in this case. The only requirement I have is that this probability, when you make the random choice of H over the family of hash function H, must equal to 1 over m to the power of k. Okay? Now when this happens, this is called K universal hashing, and these hash functions are called K-wise independent hash functions. So notice, the capital H is called K universal hashing family, and the hash functions from H is called K-wise independent hash functions. Okay? Specifically, let's look at K equal to 2. K equal to 2 is a special case, right? What this actually implies is the following. Is probability when you make the random choice of H, this is what? They are independent. These two are independent, meaning of course the random choice is still the same. And when this equal to 1 over m squared, which means each one of them must be equal to 1 over m. So this actually is a stronger argument than universal hashing. I hope you notice this, right? Because universal hashing only says this. When you have K-wise independent hash family, you automatically have this, by the way. Because for sure, right? When K is greater than or equal than 2, right? So it's a stronger argument. And another way to look at this is, in that example we construct, H0 is always equal to 0 with probability 1. So that's a universal hash family, as we argued, but it doesn't satisfy K-wise universal requirement because there's one element hashing to a particular fixed position with probability 1. When that happens, obviously you cannot have this property as required by KY's universal hashing requirement. Okay? And when this happens, when this is true, what does it indicate? That indicates if you view x and y as random variables, if you view x and y, sorry, not x and y, if you view hx and h and y as random variables, these two are independent. These two are independent. Do you follow me? These two are independent. And this is what we call two wise independent hash functions. And when any three of them are independent, this becomes three independent hash functions, so on and so forth. Okay. I think I have a So here are some properties of KY's independent hash functions. If you have a K universal hash families, then these claims are true. And in fact, part of your homework 2, the last problem in your homework 2, asks you to prove these claims. Asks you to prove these claims. Okay? So the simple observation is even two universal, K universal, by the claim above, as you can tell, K universal is obviously stronger than K minus 1 universal because K universal implies K minus 1 universal automatically. If that claims is true, right? If those claims are true. So with that being said, I only need to argue that 2 universal is stronger than universal hashing in order to convince you that K universal is stronger than universal because K universal must be stronger than K minus 1, K minus 2 all the way to 2, and if 2 is already stronger than universal, then K universal automatically is stronger than universal hashing families. So the previous construction for universal hashing does not give 2 universal as I argued for you using this special case already. Okay? But 2 universal already give you that property that any hx equal to a is probability, the probability is just 1 over m. So it's already stronger in that sense. Okay? The question is, how do you construct KY's universal hashing? How do you construct KY's universal hashing? What I want to do is to start with 2 universal hashing, then I extend this construction to K universal hashing for you. And the 2 universal hashing construction is exactly this. It's exactly like what I have shown. Now I can answer finally the question I throw to you, and I promise to answer for you, which is why this is a good hash family. Why this is a good hash function? Because it is a 2-wise independent hash function. And the family of this hash function. By the way, what do I mean by the family of this? Any random choice of A and B gives you a hash function. So when you iterate and exhaust all the possible random choices, that gives you a family of these hash functions with respect to this prime P. Once you fix the prime P. And that family of hash function is called 2 universal hashing family for any random choice of A and B you have selected from the field OP once you fix the prime P. So note that you have P squared number of hash functions. Right? You have P squared number of hash functions. Because the size of this is roughly P. You make 2 random choice, then essentially P choose 2, right? So the size is simply P squared. So how do you prove this? How do you prove this? So here is a proof, a simple proof, right? hx1 and hx2 is simply this matrix dot product between that matrix and the vector A and B. No? Right? Because that gives you A plus bx1 and A plus bx2. By the way, the notation is still supposed to be compliant with the slides. I do that, but it doesn't change anything. It's just a symbol, right? use the A to denote the second one instead of the first coefficient. It doesn't change the game at all, right? But just to be consistent with my slide over here. Okay? Do you follow me? So hx1, hx2 simply equal to the dot product between that matrix and the vector A and B. To calculate the probability hx1 equal to A1 and hx2 equal to A2, what do? You're calculating essentially this, right? No? It's you just write down, copy this down, and make them to equal to A1 and A2 as output vector. And in other words, AB equal to the inverse of this matrix multiply the vector A1 and A2. So far so good? Since A and B are chosen randomly, the chance that each of them equals some specific value is at most what? 1 over p squared. You follow me? So here I'm using a slightly relaxed argument where I do not do this. I do not do plot m. I argue in the extreme case I simply view m equal to set of prime. When that happens, that's exactly 1 over m squared as desired for two universal hashing requirements. Do you follow me? So that's the end of proof. Of course, one thing I haven't shown you is what happens if you take this and mod m. Right? You might actually increase the chance of clearing when you do that because you're essentially truncating the output space, the output domain size, right? But however, luckily for us, this modular m operation doesn't really change this probability that much. And that argument is much more involved. And I'm not going to give you that. Okay? But that requires you to have some deep understanding of linear algebra and the concept of field in mathematical sense. Right? So I'm not going to argue that for you. Just believe me, if this holds for p equal to n, it will hold for when you add another modular m operation to the end. So the probability still is roughly 1 over m squared. The probability is clearly 1 over p squared, that's for sure, using this argument. The argument is add a modular m will change this probability to 1 over m squared. That last piece is a little bit involved. I will omit that last piece. But at least up to this part, it should be fairly straightforward for you. Do you follow this argument so far? Okay? Because the only random choice here is A and B. And there are 1 over p squared combinations of A and B's. That's why this probability is just 1 over p squared. That's the argument. Okay? That's the argument. So in practice, how do you construct k-wise universal hashing, by the way? How do you construct k-wise universal hashing? Well, you simply extend this to the following. Right? Instead of, for example, this gives you 2 y's. Right? To give you 3 y's, you do this. To give you 4 y's, you do you just keep going. And that's a beautiful construction, right? Isn't it? Right? Just keep expanding this polynomial. Keep reading x to 1 more power. Then you're getting another k-wise. You're gonna get k-wise universal hash. And the proof, actually, if you think about it, is similar to this. Basically, you look at the probability that two polynomial of this form, what's the chance for a polynomial of this form to evaluate to the same value? Consider these are curves, right? In other words, how many times this curve is gonna collide, gonna intersect? And from a geometry point of view, that's how you view this. Right? A polynomial is a curve, right? You understand what I'm saying? No? Okay. right? Polynomials. This is contribute to, I think, Descartes, this French guy, right? He invented the modern geometry, right? So curves are fundamentally the same as functions. When you write a function, you are essentially drawing a curve. So I could be bad at drawing, but once I realize this, I'm an artist too. Because what I wrote on board are essentially these beautiful curves. So I'm an artist too. So what we're doing is we're looking at if you randomize these parameterizations. The parameterization here is what? Those A and B and C, right? If you randomize your choice over the parameterization of those curves going to collide at most with 1 over p squared, 1 over p cubed, 1 over p to the power 4 probabilities. Why? Because they have at most this many collisions. And when you randomize them, that's essentially equal to the collision probability. That's the intuition of the proof, roughly. Okay? That's the intuition of the proof, roughly. Okay? You follow me? Alright. That's it. We're done with hashing. One last piece of argument I want to present to you is, obviously, the best hash function you can hope for is what? For a size n input, what is the most powerful hash function you can ask for? What's the most powerful hash function you can ask for when you know your input size is n? It's n universal hashing, right? Does that make sense? And what does it translate to human language? What's the n universal hashing? What does the n universal hashing mean? What does the n universal hashing mean? That means for this input, you design the hash function such that the output is totally independent from each other. The output is totally independent from each other. Right? That's essentially what it means. But this is super expensive, as you can tell. This requires you to get this, you need to do. And this is expensive to do, right? Because first of all, the size of this hash function is what? To describe this hash function, you need at least n values to remember the n parameters. And to compute this hash function, hx, you need to raise x to the power of n minus 1. By the way, what's the cost of CPU cost of doing this? Can someone tell me? Michael? Huh?
You can do it in logarithm.
You can do it. It's not. Some of you may argue, oh, I need O n time because I need to multiply x n time. No, you don't. You do exponential by squaring. You can do this in log n time. The idea is you do x squared, x4, x8, so on and so forth. This x4 is essentially x squared equal to x squared. This is x4 times x4. So you only need to do roughly log n number of multiplication instead of n multiplications. But still, it is expensive, right? Expensive. But it does give you n total independence, meaning I take all of you, I've input a hash. Clearly, this group has strong correlations. Why? Because all of you are CS students. So the input has strong correlations. But somehow, magically, I can design the hash function after this hashing operation. All of you have no correlation whatsoever. All of you are totally independent from each other. Even though all of you have a strong interest in computer science. That's a very strong correlation to begin with. But I can destroy that correlation almost totally by using n-universal hashing families. But it's super expensive. So typically in practice, oftentimes a k-wise universal hashing is good enough for some small constant k. However, I do want to remind you, k-wise and k plus 1-wise universal hashing are totally different. There is a strong difference between them. And I can argue that for you by using this simple example of 2-wise versus 3-wise. So what I do is the following. My input x and y, my hash function is this. inclusive OR. So can we construct this table now? Can someone fill this value for me? What's 0 exclusive of 0? Well, if you don't know this, I think I should wrap up my lecture and be done with all you. Because I don't want to teach computer science master students who don't know exclusive OR operation. Come on, give me a break.
0, 0, 1, 0.
Huh?
0, 0, 1, 0.
0?
0.
0? 0? Okay. Oh, simply, can you come up and fill the board for me? Exclusive OR, right? You all should know what exclusive OR does, right? No? Yes or no? Sure about this?
0, 1, 1, 0.
All right, yeah.
Okay. Exclusive OR says if two are the same, then output is 0. If two are different, the output is 1, right? You follow me? Okay, so what's interesting about this is that if you do the math, if you look at this, any two of them are independent, but any three of them are not. Okay? Any two of them are independent, but any three of them are not. So this shows you the subtle difference between 2Ys and 3Ys. Okay? I leave this as a brain teaser problem for you to think about. Why any two of them are independent but not any three of them. Okay. Alright, let's move on to the next lecture. Okay, so we're finally done with hashing. It is non-trivial discussion, but I feel pretty good about covering all this. Next time when you interview with Google or Microsoft, at least you can claim one thing, which is you know hashing inside out. Because that's pretty much all you need to know about hashing. Yeah, that's pretty much all you need to know about it. And I bet the people who interview from Google or Microsoft may not know a lot of stuff we covered. I mean, if he asks you, oh, universal hashing, you answer that, you say, oh, can I ask you perfect hashing? See whether he understands. Okay. Or dynamic perfect hashing. Can you do that? You can challenge him or her back. But of course, I don't recommend you to. I did that once with one of my interviewers and got declined because it's perfect. But I did that because I don't want to go to that place in the first place, which is Google. I have a faculty offer at that point, so I kind of played the game a little bit. So I don't want to go, so I use that trick. But anyway, so B plus tree, okay. So we talk about hashing index structure. Next we talk about tree indexing structure. To remind you, what we said is for indexing structures, everything starts with data entry, right? And you have one data entry per record. You have one data entry per record, right? You have one data entry per record. And what you do is you take the search key value k out of that record, and there are three alternatives. Either you take the record itself as the data entry, or alternative 2 is you take the search key value k and RID. Alternative 3 is search key value k plus a list of RIDs. Right? So those are the three alternatives, but those are data entries. And then you build a tree structure out of these data entries. And before I talk about that tree structure, I want to show you what index entries are. Index entries are those entries that go to the intermediate level of the tree. Right? The leaf level contains only the data entries, but the intermediate levels all the way to the root contain index entries. The index entries. Okay? The index entries. So what you do is you look at, and what you do is the index entries are somewhat very similar to the data entries, right? So most index entries are of the following format. You have a key value, search key value k, and a pointer p. The pointer p here is nothing else but a page ID. A page ID. basically for you to look up a page from the level down below. Okay? But the only special case is you have this leftmost pointer P0 there. It doesn't belong to any index entry. And I will explain this in further detail later on. But this is nothing special compared to, if you think about, if you just think about a binary tree construction. What's a binary tree? For example, a simple binary tree is like this. If you think about it, I can argue, you know, this, I can imagine these are my data entries. That's RID, pointing to the record with 30 values to 5 and 15 respectively. And this is my index entry. And this index entry, if you think about it, it can be viewed like this. This is your page ID, which gives you this page right here. And the leftmost pointer P0 is essentially this one right here. So what we're doing here, but we're not doing a binary tree. All we're doing is to expand this index node to contain not just only one entry but multiple entries. Why we're doing that? Because we're in the external memory model where a page size is much bigger than containing just one entry. You can hold multiple entries. Because whenever you visit this node, it's one I/O. You can, of course, put in only one index entry per page, but that's a waste of your I/O bandwidth. When you're paying one I/O, you better load multiple entries rather than just one entry. So that's the motivation of designing an index page with index entries like this. Simply expand your binary tree construction to multiple entries. Okay, so that's the intuition. And I will start with, just like hashing, I will start with a static construction, then go with a dynamic construction. And this is called, the static construction is called ISAM. Index sequential access method. Before I go, I will run a simple experiment to you to show the power of index. I hope this experiment works. I haven't done this experiment for a while, so I hope this works. Actually, I'll just go here. How come it doesn't show it? It's here. So I will do a simple experiment and then go with presentation mode. Okay, so in this case I'm going to use MySQL. Okay, and I have a database called CS6530DB, and I will show you the tables. In particular, I'm going to use test 1, test 2. And I'll show you the schema of test 1 and schema of test 2. They are identical, as you can tell, ID, name, and rating. Right? So each person had ID and give a rating for that person. Very simple database. And each, I believe, has a mean of 5 million records. 5 million records. So it's not big, but relatively sizable tables. Right? Not something that's small. Okay? And then I will show. So create table test 1. And what you notice is this shows you how this table was constructed, defined. And you notice that there is a B tree, BT stands for B tree in MySQL database. There's a B tree index on ratings column. Okay? And if I do the same for test 2, you notice that there are no such B tree on the rating column. That's the only difference between the two tables. Data-wise, I mean the value-wise and size-wise, the two tables otherwise are identical. Do you follow me? Yes or no? Okay. I'm going to do a simple experiment. do this from test 1. We're reading okay? So rating is a value between 1 and 100, by the way. I have 5 million records. So I'm selecting about 4%. So let me change this to 5%. Okay? So I should expect about 250K record output. If my rate collection is, I think it's 5 million. Okay. Scoring. Okay, 25K. Right? So I'm gonna run the same query from test 2. Oh, something's not right. Let's try this again with test 1. Okay, count might not work. Let me do this. Let me select. Okay, let me do this now. Hope this time it works. And let me do the same for test 2. So as you notice, there's a huge difference in performance of the two, right? Does that make sense? You notice there's a 6 second versus 1 second, right? And what is reason for that? The reason is because of difference in index, different index. And we're using index on one table but not the other. And that results in a huge performance difference. And I will explain to you why we have such a difference using the remaining part. Obviously we won't have time to cover all of this today, but I convince you there's a huge difference between using versus not using index. Okay. So first of all, I'm going to show you the static data structure called ISAM. So the idea is as follows. Illustrate using this simple picture here. I have a data file with many data pages. That's your heap file right here. Okay? Okay? Suppose I have n pages here. And what I do is I take the value out. Take the value out. Actually, using our notation in this class, I should change this to n or b, right? Because we have n item, n record in total, and the size of each page is b, holding b records, so total of n over b pages, in my heap file. What I do is I make suppose I'm using alternative number 2, which means my data entry is a search key value plus RID. So these are my data entry 1, data entry 2, data entry 3, data entry 4. Referring back to the first record here and the record here, the record here. You may wonder why the order of the data entries are different from the order of records, because you see the pointers crossing over each other, right? The reason is we sort these data entries by the search key value. In other words, the pages here are not necessarily sorted by the search key value of the records, but in the data entries we do sorting first before we do anything else. we sort the data entries based on the search key value. That's why you see the pointers start crossing over each other. Okay? Then, very simple, I group those data entries into pages. I group those data entries into pages, and that's my leaf level pages. And I suppose I have n number of pages. How do you get this value of n? Well, it's n divided by b prime, as I explained last time. Why? N is the number of data entries you have, because for n records you're going to have n data entries. And b prime is some value that's greater than b, obviously, because b tells you how many records you can hold in a page, and b prime tells you how many data entries you can fit in one page. Given the same page size and the observation that data entry size is much smaller than record size, b prime must be much bigger than b. So which means the observation is this must be less equal than this, obviously. Okay, n over b prime is much less than over b. So that's your leaf level. And how do you construct level above? Well, you take the smallest search key value out of each page. You take the smallest search key value out of each page. And you construct an index entry for every such key value. And you skip, by the way, you skip doing so for every b prime number of index pages. For example, the first page, you don't take the search key value out. Rather, you take the search key, the k prime 1 is coming out from leaf page 2, the smallest search key value from leaf page 2, and make an index entry out of it. So that's the search key value for that index entry. This pointer is simply the page ID of leaf page 2. And this is the smallest search key value out of leaf page number 3, and this pointer is simply the page ID of that page. You don't do this for the first one because you have the leftmost pointer for the index page. And that happens roughly every b prime number of index entries. Suppose index entry are the same size of data entry. If you have b prime number of data entries per page, per leaf page, you're going to have b prime number of index entries per index page. So every b prime number of them, you skip doing this for one page because you have that leftmost pointer for that index page, then you do this. So you get n number of entries, obviously. You get n number of entries because you have n pages. And this goes to roughly n over b prime pages. If you do the math, this becomes n over b prime squared number of pages. And you basically recurse from there. You keep doing this until you have only one page left. You follow me? And how many levels do you have? If you do the math, how many levels are you going to have? Well, you keep doing this until you become 1, so this is simply what? You start with n, right? And each level you reduce by a factor of b prime, so it's log b prime over n. So roughly you could log b prime of n over b. Okay? That's the height of the tree. And this is the static data structure in the sense that later on if you have insertion and deletion, that explains this overflow pages here. Because in the leaf level, you need to make those data entries sorted in order. But if you are inserting a data entry into a page that has no space left, because of the static data structure, you're not going to reorganize the tree, so you end up attaching an overflow page to that leaf page. Okay, so this is an example. And I will stop right here, and we'll continue on Tuesday. So this is the static data structure. And the challenge, though, is that we will potentially have a large overflow chain at the leaf level. And we will talk about the dynamic structure of this. By the way, lab 2 is to implement this index structure. Of course, using these page models. With that being said, I will stop right here. Okay, thanks.
인베 순서야. Yeah. I'm not sure. Never had it. Yeah, I just got something over in the house. Oh, what's wrong with it? Wow, it's kind of something.